Hello and welcome to a quick video on how to calculate empirical formulae. This would be good for students who are doing the IB as well as students who are maybe in grade 10 or year 11 who are studying mathematical concepts in chemistry. The key part for IB that it refers to is from Unit 1, which is all about stoichiometric relationships, and it's in particular part of Unit 1.2. And the statements that it refers to, which is relevant in this video, is in the understanding section. It's the principle of what the empirical formula is, which is the empirical formula, molecular formula of a compound give the simplest ratio and the actual number of atoms present in a molecule respectively. So we'll cover that today. And for the application and skills, it's all about the interconversion of the percentage composition by mass and the empirical formula. So it's basically how to calculate empirical formulae full stop. So let's start off with what these words empirical and molecular formula actually mean. So first off, the empirical formula is the lowest whole number ratio of atoms in a compound. It's the simplest ratio. The molecular formula is different. The molecular formula is the true number of atoms of each element in the formula of a compound. So one way of thinking about it is the molecular formula is your empirical formula, that simple ratio multiplied by a number which we'll call n. So for example, let's consider benzene, which is C6H6. The empirical formula is CH, but if you multiply that by n, which in this case is 6, it gives you the molecular formula. So that's what empirical formulae are. And if we consider ionic substances, because they're always massive lattices, the ionic compound that we have as a formula is always the empirical formula. So for example, we have NaCl, sodium chloride, magnesium chloride, aluminium sulfate, and potassium carbonate. Those are the simplest ratios, even though they are the formula that we usually use for them. They can't get any simpler than that. Molecules are a bit different. So if you've got a molecule, they might be empirical, they might not. It depends on what numbers you have. So for example, if we consider H2O and we try and simplify that ratio, we actually can't because the smallest number we have there is 1 for oxygen, so it's going to stay as H2O. If we consider glucose, which is C6H12O6, we can actually simplify this because each number is divisible by 6, and that should give us CH2O. And if you consider this molecule, C12H22O11, it's actually the same, the empirical formula is the same as the molecular, because you can't actually divide the numbers by a common factor because of that 11. So that's the basics of how to do it. Now the kind of questions which you're likely to encounter will be a bit more complex than just determining it like that. It'll look something a bit more like this. So this is a typical question. Analysis of a compound found in an iron ore determined that it contained 44.8 grams of iron and 19.2 grams of oxygen. Find the empirical formula of iron oxide. Now for this type of question, you can sometimes get a bit stumped in an assessment situation, not know where to begin. I like to use a rhyme to help me remember it. And the rhyme goes a little bit like this. It goes percent to mass, mass to mole, divide by small, and multiply to whole. Now that doesn't make a great deal of sense at the moment, but with a couple of examples hopefully it will. Now let's use the question that we used before and let's try and solve it. Now I like using a table to structure my information, and it looks a little bit like this. Okay, so let's have a look at it. So in the table, as you can see, I have the elements in question, which I'm going to be solving in my question. I've got mass, AR, moles, and ratio, and then finally the empirical formula. Now you have to just go through this stepwise. So let's begin. So first of all, I need to work out the actual elements which I'm dealing with here. So I've got 44.8 grams of iron and 19.2 grams of oxygen. So the iron, the symbol for the iron is Fe over here, and over here is oxygen. So I'm just going to put O. And now I'm going to put the masses. Now the masses are here. So I've got 44.8 grams, so I'm going to put 44.8 there, okay. And for the oxygen, I've got 19.2. One handy thing you might like to do is to underline that information in the question before you actually attempt it. I'm then going to put the AR in. Now the AR can be found in a number of places. I like using the data booklet for IB. Woohoo, very exciting. And if I look at it, I get really precise numbers. So Fe is 55.85, so let's whack that in. 55.85. And oxygen is 16.00. Okay, now my first step of my rhyme is percent to mass. Now, there's no percentages here, and we'll do that in the second problem, so I'm going to leave that blank. I'm going to move to my next bit of the rhyme, which is mass to mole. Now, if you're sharp from previous learning, you should know that mass divided by MR, or AR in this case, gives you mole. Okay? Now, my mass is 44.8, so I'm going to divide that by 55.85, and that gives me 8 divided by 55.85, 0.802. Now I can do the same thing here. My mass here now is 19.2. I divide that by 16, and that gives me 1.2 exactly. Okay, so that's my step. So I've got the number of moles of iron and the number of moles of oxygen. The next part of the rhyme is divide by small. Now you want all of these mole numbers basically as integers, so you can work out what the ratio is between each atom. My smallest number is 0.802 for iron, so I'm going to divide that by itself, and that's 1. Now if I do the same thing onto this side, remember I have to divide by small, so I'm dividing by 0.802, and that should give me 1.5. Now you might find it be like 1.49 or 1.51. That's okay, as long as it approximates really closely to something like 1.5. The problem here is that I've got non-integers now. I've got 1 and I've got 1.5. So the final part of my rhyme is multiply till whole. So to multiply till whole, I can multiply both numbers by 2 in order to make that work. So 1 times 2 equals 2, and then 1.5 multiplied by 2 equals 3. So now I'm pretty much finished. You can see that the ratio of atoms is 2 to 3. So my empirical formula is Fe2O3. That's my empirical formula. All right? So that's the example if you're given masses. Now sometimes instead of masses you're going to be given percentages. Now the principle is exactly the same. The one thing you have to remember with percentages is you have to consider it almost as if you've got 100 grams of the substance. Now if you've got 100 grams of the substance in this particular example, it would mean that instead of having 75% of carbon, you've got 75 grams. And if you've got 25% of hydrogen, you've got 25 grams. So let's again, with this particular example, put the information in a table. So we're going to start with C for carbon and H for hydrogen. And let's put the numbers in. Now I've got 75% for carbon and I've got 25% for hydrogen. The AR of carbon I think is 12.01. Yep. And for hydrogen I think is 1.01, which it is. Okay. So I've done percent to mass, which is basically this first step by putting the percentages in. And now I have to do mass to mole. Alright, so that's my next step. So I've got to do 75, which is my mass or my percentage, divided by 12.01, which gives me 6.245, if you like. And then here I've got to do 25, which is mass or my percentage, divided by the AR, which is 1.01, and that equals 24.75. Okay, now I have to do divide by small. Now the smallest number here between 24.75 and 6.245 has to be this one. So I'm going to divide by that number. Which equals 1. And I'm going to do the same thing on this side, 24.75 divided by 6.245, which I believe is 4. Okay, or more or less 4. So I've got 1 carbon and 4 hydrogen, so the solution is CH4. Okay, so it's as simple as that. So what I'd like you to do now is I'd like you to have a go with this problem. Please pause the video now, attempt it, and then we'll go for the answer together. I'm assuming you've just paused it and you want to see what the answer is, so let's go through it. So I've got carbon, I've got hydrogen, I've got oxygen. First step is percent to mass. That doesn't count for this problem, so let's go straight to mass to mole. Now the mass of each is 2.4, 0.4, and 3.2. The AR of oxygen is 16.00, hydrogen is 1.01, carbon is 12.01. The moles is 2.4 divided by 12.01, and that equals effectively 0.199, which is basically 0.2. Here it's 0.4 over 1.01, and that equals 0.396, which is basically 0.4. And here I've got 3.2 over 16, and that equals 0.2. Okay. I then have to divide by small. My smallest number is basically 0.2. Now that these both have 0.2, this is probably a little bit smaller. So that divided by itself equals 1. This number divided by 0.199, they're pretty much the same number, so that's basically 1. And then 0.396, which is basically the same as 0.4, is divided by that, and that will give you 2. So what you should have here is CH2O. Alright, let's have a go at another one. Here's your final problem. Again, I'd like you to pause it, have a go at it, and then we'll go through the answer together. Okay, I'm hoping that you've had a good go at that, so let's go through the answer and see what we got. So I've got iron, and I've got oxygen. So the first thing is percent to mass, so I'm going to assume I've got 70 grams of iron and 30 grams of oxygen. Next step is mass to mole. I've got the AR of iron, which is 55.85, I think, and oxygen is 16.00. Yes. And then I have to do mass to mole. So mass to mole is 70 divided by 55.85 equals 1.253. And for oxygen it's 30 over 16, which equals 1.875. Now, in order to do the next step, I have to divide by small. So 1.253 divided by itself, because it's the smallest number out of the two, is 1. In this case, 1.875 divided by the smallest numbers, which is 1.253. That will give you basically 1.5. Alright. Now I need to multiply to a whole, so I have to basically double them. So 1 times 2 equals 2. And here 1.5 times 2 equals 3. So the answer is Fe2O3. And that's your answer. So, I hope this has been helpful. And best of luck with doing more practice problems around empirical formulae.